Hello, everyone. My name is Andrea Johansik. I'm a program specialist with the Emissions Neutral Buildings team at Alberta EcoTrust Foundation. And I'd like to welcome you today to the ENBIX webinar, A Commercial to Residential Conversion in Alberta, Neoma Case Study. Before we begin, I would like to take some time to acknowledge that I'm joining today from Treaty 7 territory, which comprises the Blackfoot Confederacy, Siksika, Piikani, and Kainai, the Tsuut'ina First Nation, and the Iarhe Nakota Nations of Chiniki, Bearspaw, and Goodstoney. The city of Calgary, which is where I'm joining from, is also home to the Métis Nation of Alberta, Districts 5 and 6. For me, doing this acknowledgement is really a recognition of the many diverse Indigenous peoples that steward and care for this land, which does include the land that the Neoma building, the subject of our discussion today, stands within. I just wanted to take some time to introduce folks that are new to Alberta EcoTrust Foundation. If you're not familiar with Alberta EcoTrust, we are a charity best known for grant making, cross-sectoral collaboration, and capacity building in our three focus areas, which are nature-based solutions and conservation, climate resilience and emissions reduction, and the circular economy. Alberta EcoTrust is the host organization of the initiative ENBIX, which stands for the Emissions Neutral Buildings Information Exchange. And our goal at ENBIX is to accelerate building and renovation practices that lead to an emissions neutral built environment for both new and existing buildings across Alberta. And Alberta EcoTrust does have another really exciting initiative just starting up. And I'm going to pass things over to my colleague, Didi McCarr, to just spend a few moments introducing the Retrofit Accelerator Program.
Hi everyone, I'm really excited to announce the Alberta EcoTrust Retrofit Accelerator. It's an initiative of Alberta EcoTrust Foundation and is funded by Natural Resources Canada under the Deep Retrofit Accelerator Initiative. A deep retrofit is a holistic approach to upgrading buildings either through a single project or a phased approach that achieves meaningful GHG reductions. And our program is aimed at supporting commercial, institutional, and multi-unit residential buildings throughout Alberta who may not have the existing resources to prioritize energy retrofits. Our program will be providing support and guidance from the initial interest to project completion for these deep energy retrofits. And our coaching will help building owners make informed decisions on capital planning and support them throughout the entire process. A couple of initiatives that we have through this program will be free of charge coaching services. So kind of that external energy manager that will be able to step in and provide access to information about project planning, management, and decision-making support. And then also supporting with identification of financing and navigating through that. We will also be providing access to partially funded studies, including energy assessments, decarbonization plans, and business case development. Our project was funded again by the NRCan's Deep Retrofit Accelerator Initiative, and we're currently in the soft launch phase, starting to roll out some of our project deliverables, and we will be having a full launch in the fall 2024, so expect more information to come out then. Our program does end currently in March 31st, 2027, so stay tuned for more information.
Great, thanks so much, Didi. That's awesome. Oops, I'll go back here. Yeah, I'd like now to introduce our speaker, Heather Elliot. Heather is a senior associate and building envelope specialist with Entuitive with over 13 years of experience. And her work ranges from new construction to remediation, retrofit of a wide variety of building types where she employs practical solutions to ensure building lifespan and maximize performance. Heather is currently working on various office to residential conversions in Calgary and has been part of multiple feasibility studies looking at viability of conversion or recladding, retrofitting. This is such a relevant conversation, I think, in Calgary, but also in cities across Canada, really, as our downtowns change and we experience housing shortages, Heather. So I'm super excited to learn from you, and I'll just ask you to take it away from here.
Perfect. Okay. Well, hello, everyone, and thank you for having me. Appreciate the introduction, Andrea, and we will get started here. So today we're looking at a conversion conversation. We're going to be looking at Neoma, which is a project here in Calgary, commercial to residential conversion. We're also going to be looking at another project in on the east side of Canada, just as a comparison. And then at the end of the presentation, we're going to talk a little bit about retrofits in Alberta and what we kind of think makes sense for those. We already had a great introduction in terms of who I am. I'm a senior associate here at Intuitive in Calgary. I've worked in Alberta, Saskatchewan, and a little bit in the United States as well. And across our company, we're sort of throughout North America in a way. So we've touched a lot of building envelopes and other pieces of buildings all over the map. Something that has become really interesting to us is conversions. We're seeing that in Calgary downtown, especially right now. It's very interesting. We're at a bit of the forefront in Calgary, just having a downtown core with an aging building stock and quite a bit of empty space and determining what to do with it. So you're seeing a lot of thought and feasibility studies and discussions about potential conversions. And we're now starting to see that in other large cities as well, Ottawa, Toronto, other large cities, just considering this in the States as well. So very interesting from that point of view. Again, just a quick overview of our agenda. We're going to be looking at Neoma, then we're going to switch gears and look at Soble, which is a true deep energy retrofit, just as a comparison to the Neoma conversion. Kind of same, but different. And then at the end, we'll talk a little bit about retrofits in Alberta specifically. So let's jump into Neoma. If you don't know it, and if you are from Calgary, you might remember Sierra Place, which was an old downtown office building. It is now Neoma. So that is where that one sits. And just as a quick introductory slide, why are we even talking about conversions? Why are we talking about decarbonization? Why are we talking about retrofits? It's that reminder that buildings are a big piece of that puzzle in the world. And a quote that I think is really interesting from Architecture 2030 and that we keep rolling back to at Intuitive here is that 2/3 of the building area that's out there that exists today will still be there in 2050. We are not going to build enough new buildings to overtake that. So to meet targets and hit targets that everyone is talking about for 2030 or 2050 or beyond, we would need to retrofit a building every minute to actually achieve that. And that's not what we're doing right now. So just to put that in perspective, in terms of how much building stock is actually out there that is going to be there years from now, it kind of puts it into perspective about why retrofit has to be at the top of everybody's list when we talk about decarbonization and thinking about emissions by sector. Buildings is a big one. So here's Neoma, the nice glossy end photo here. A little bit about the project. Our client was Home Space. Intuitive, our role was prime consultant, building envelope and structural consulting as well. Shout out to development manager was M3, architect Gibbs Gage, mechanical and energy modeler was Reinbold, electrical was Nemetz and Associates, and then the contractor was PCL, and they were brought in quite early on the project, and that was really important from a pricing perspective and actually getting things through building permit and into construction very quickly. $30 million budget, and that's sort of what prompted this this conversion. Was that team came together. We knew that Home Space and In From the Cold wanted to take a look at Sierra Place. They had the property and they knew that they wanted to do something quite drastic with it, and they hired this team to take a look at it from a feasibility study point of view to begin. So you can kind of see old Sierra's Place versus what this is today. So this was a 1950s vacant downtown commercial building, kind of coming out from the COVID quiet times. Just there was no tenant in the building. It was converted to a residential occupancy, so now it provides a homeless shelter at the lower floors and administration, and the low-income housing at the upper floors. Any good conversion needs to start with investigative assessment. So that's the biggest part, I think, to take away, is that you can't just jump in to a conversion. There's a lot of questions about the existing building, multiple site visits, given the fact that they don't necessarily match their as-built drawings. We all know how that goes. If you're in the construction space, you might have a set of drawings and expect one thing. That's not what we find on site. So a lot of exploratory was done in this case to develop a feasibility study and even to determine, is this building even a good candidate for conversion in the first place? Something that you should be thinking about would be reviewing the potential for occupancy changes, that's architectural changes, code changes, egress, all of those things. Balcony additions, especially in a conversion to residential. There's a big question about, do you add a balcony? Do you add operable windows? There's all these questions that kind of come along with it. Facade upgrades. At Neoma, they were considering solar voltaics, so looking at integrating solar potentially into the facade. They didn't end up going that way, but we looked at it in feasibility. So there's a lot of different options you can think about from a facade perspective. And then obviously modernizing mechanical and electrical systems is a big piece of a conversion. And so what makes a good candidate? This one was interesting because the schedule was very aggressive. So funding on this project was subject to hitting some milestones. So this was actually the fastest development permit and building permit in Calgary's modern history. And it was sort of fast-tracked based on the fact that this building was a very good candidate and that the city of Calgary specifically wanted to see conversions starting in the city. So that was a benefit that this project had. But in terms of what makes a good candidate, you have to think about your limiting distance. So how deep are the floor plates? Is that going to translate into feasible residential units? Do you have stairwell placement that will allow for your code required egress, dead end hallways, those things like that? There's solutions if you don't have the floor plate, but they're going to impact building efficiency. They're going to be potentially troublesome. The building envelope window wall ratio. So this is key. Full replacement is costly. So if you were looking at a building, if there's ribbon or punch windows available, that would be easier and likely cheaper in terms of replacing it with operable glazing. From a structural side, the building structural system is really going to drive the unit planning. You know, what can you do from a residential unit perspective? Post-tension systems aren't a deal breaker, but they're going to require a very detailed map, and you need that post-tension system to be in good condition, obviously. And seismic and vibration behavior are also quite important. Retrofitting it is extremely costly. So if retrofit is not required or minimal, that makes a great candidate from a seismic perspective. HVAC systems, you really have to think about just how much of the existing system can even be reused and will it even matter. Generally, for a residential conversion, you're going to be abandoning floor distribution systems and moving towards like a unit-based layout, but having a good quality base system goes a long way to helping with like the overall budget and what you actually have to do from an HVAC perspective. And the same kind of goes for electrical as well. And then the big one, occupation, or whether it's occupied. So an unoccupied or partially occupied building would obviously be a better candidate for conversion. You can kind of see on the next slide, it's obvious, taking an existing office floor plate and converting it to residential partially occupied would be quite difficult. So Sierra Place was a great example of basically an empty shell that was just ripe for the picking. So it was a great candidate from that point of view. So a couple challenges and solutions that we kind of went through in feasibility that I thought I'd share just as an overview from the building envelope side. The old curtain wall systems, that was really the big problem. So I mentioned that what makes a good candidate is having ribbon or punch, because that way you can keep the efficiency and actually add an operable window relatively easy. In this case, they had older curtain walls from the 1950s. They lacked thermal breaks, so they decided at the end of the day to replace those, but instead of replacing them in kind with another window wall or a curtain wall, they actually ended up replacing those with new stud framed walls between floor slabs with an opaque cladding system. So we essentially took what was a full scale curtain wall style kind of floor to height glazing and basically created it into a punch opening system. On the elevations where there was existing brick and strip windows, those are actually remained in place, just new windows there. And then we completed isolated brick masonry repairs on those elevations. So that's mortar repointing, isolated brick unit replacements, that sort of idea. And then at the end of the day, the roofing was actually found to be in decent condition. It had been replaced relatively recently. So there was a decision made to just replace the mechanical penthouse roofing system and leave the rest of the roof in place. But that's just one example of just moving through different details. From window perspective, you can sort of see the differences here. So we've got a brick section as well as a typical wall section. So you're essentially rebuilding with an exterior insulated system between floor plates, where that detail on the right there, detail 8, would have previously just been floor to height glazing. So that was the big change on Neoma. And you can see on the left-hand side just some of the revisions that had to be made and some of the alterations that were made for those new operable strip window style, kind of between the existing brick and leaving the brick in place to be able to actually make that happen. And from that perspective, where does all of this feasibility information end up? One of the big deliverables kind of at that feasibility study or following the feasibility study was an energy model. So Reinbold, our mechanical team, put that together. From a building envelope perspective, you're looking at inserting U values from a reference building, comparing them to the existing building, the Sierra's Place building, and then the proposed Neoma retrofit. So it was kind of an interesting exercise where you can compare back against the reference building, but you can also compare back against the existing building. And that's important just from a greenhouse gas emissions point of view, just being able to understand, like, yes, you're improving upon the reference building, you're also improving upon the existing building in a different way. And so there's a lot of iterations and options that go into this. You can also kind of see the example of, say, like the roofing or other items that remain the same. So as an example, you can see the below grade roofing, waterproofing that's listed there is the same for the existing building as it is for the proposed, versus other items that have very clearly changed between the existing and proposed. So that's always interesting when you're dealing with an existing building and kind of working through those iterations of what you can actually improve. For this project, the low-hanging fruit would have been that, if we weren't meeting the targets that we were planning to meet, even if the roofing was in decent condition, we could have added additional insulation to the roof and improved the envelope even further. That was sort of our low-hanging fruit option. That was also run at the time of feasibility, and it was determined that at the end of the day, we were getting the results we wanted, and so we ended up moving towards leaving the existing roofing in place other than at the penthouse. And I see one question there, just how did you assign the existing building values for performance? Was there any discussion for functional testing? I can answer that here. So partly this was based on the exploratory, so understanding as-built versus exploratory, what kind of thicknesses of insulation were we actually finding, and then assigning U values based on the exposed assemblies. So there is a bit of it's a bit of an art, not a science some of the time when you can't expose. So say like below grade, for example, you're basing that on the drawings. You might not have exploratory at every single opening, but you're making assumptions kind of based on what you've seen. Structural side, in terms of a challenge that comes up on conversions, so the seismic code implications that I spoke to earlier, this does pose a challenge. It's extremely costly to do some of the retrofits potentially. So knowing upfront whether that's going to be a problem is really important to whether it is a good candidate for conversion. So in Neoma's case, proactively and kind of part of the feasibility study, our structural team completed a lateral analysis. So that was based on the current code and determined that retrofitting was not required. And that's why Sierra's Place became such a high candidate for conversion. So at the end of the day, the only recommendations that we're really making structurally would be to repair members if we were to find any distress during demolition, for example. They did end up reinforcing some select members for localized infill. strengthening of the main floor framing, because it does kind of, you'll see it in the renderings and in the final photos, it does sort of change more to like a retail style podium level, and strengthening the roof framing for changes in loads, such as changes to the mechanical system, different units being installed, etc. On the mechanical side, so there was quite a few different options and things discussed during feasibility. This is just a snapshot out of the report. It's by no means all of the items. At the end of the day, really what they were looking at was demolishing everything in the existing basement. So all the mechanical systems just got taken out. They removed the existing rooftop air handlers and chiller. They ended up repairing an existing sanitary sewer service. And then from a swap out point of view, they were installing 3 new boilers, additional makeup air units for the stairwells and others, a new below grade stair pressurization fan, below grade smoke exhaust system, fire booster pump, domestic water booster pump, new hot water heaters, and then all obviously to accommodate the residential unit usage, you're installing new plumbing, distribution, in-suite heating, and ventilation, all to accommodate that new occupancy. So from that point of view, it's a really large, like it's an overhaul of the mechanical systems. And so you're really just, again, looking at what can go, what can stay. You can see on the next slide here, just an example. So there were certain things that they decided to leave in place. So like as an example, the cooling plant, like the existing air-cooled chiller was just left in place. So you can see if you compare the existing building to proposed, it's the same. Versus the heating plant, you can actually see the difference between the existing building with an 80% efficiency boiler, going up to a 95% on the proposed building. So there was opportunity to make improvements, but where the system actually could be maintained and could work, they actually did leave some of the existing mechanical components in place. Electrically, very similar story. So we're looking at upgrading services, but also looking at replacing the main distribution. Again, you're looking at shifting into a residential unit style occupancy layout. So a lot of changes have to happen for that. New life safety systems, backup life safety, common area lighting and power completely replaced, fire alarm systems completely replaced, security, access, communications, all completely replaced. So there's a lot of changes electrically that go into a conversion. Makes sense. And then from an energy modeling point of view, again, just a very simple snapshot. You can kind of see the difference between the reference building, the existing building, which in a variety of cases is sort of poorer performing because some of these components are older, versus the proposed building, where in most cases you're improving your performance above the reference building and also above the existing building. So that was sort of the aim here, was to do a complete mechanical electrical overhaul combined with a major envelope reclad, but with the benefit of not having to spend a lot of the budget on our structural system, since we didn't have to retrofit majorly. At the end of the day, what did the model say? So our proposed design demonstrated that we would see a 37% reduction in energy consumption. That's compared to the existing building. And then compared to the reference building, we're looking at a 17.4% reduction. And most importantly, from this point of view, we're talking about emissions neutral, right? So we're looking at a 22 almost % decrease in greenhouse gas emissions. So that was a great result from that point of view. This was meeting the requirements of the CMHC National Housing Strategy, which was sort of the funding model that this project was operating within. So they met the requirements, and so they moved forward after feasibility. At this point, PCL was actually already involved, and that was a great thing to have for a conversion. And I think conversions in the future are going to know that having that contractor in at the beginning was paramount, honestly, because you're dealing with so many existing conditions. You needed someone to do that exploratory who then really understood what the existing building was like, and could actually price out and budget and understand what you were going to be doing as part of the conversion. So for this project, costs were coming in around 20 million to start. It ended up around 28 million, but you can really see where the bulk of the costs are. even in those initial estimates. It's really sitting in our mechanical envelope and electrical costs, followed by interiors, and then really everything else is just the good looking stuff on the interiors. But really, at the end of the day, we were spending the most time on M&E and envelope. So a couple construction slides from that point of view. These are those new opaque walls being built, so you can see the existing curtain wall has been completely removed, basically new sheathing, membrane, new windows are going to be popped into those punch openings. You can kind of see the progress there. There's also a view on the other elevation with the strip windows with brick. So again, you can see the infill occurring there with new punch window layout, kind of moving through to cladding installation. On the inside, same thing. We're seeing a lot of new piping insulation, domestic water, everything just sort of being replaced in kind. Like I said, the basement completely basically wiped out, demolished, everything removed. And at the end of the day, rendering versus real life actually turned out to be very accurate, and that's not always the case, so it's nice to see. So that's a little bit about Neoma. I'm just taking a quick look at the questions before we move on into Soble. So in terms of costing out a deep energy retrofit, we looked at it very briefly at the beginning of a feasibility study, but it was determined that really for this project and the funding model that they were going after in terms of the dollars and cents that they were hoping to be granted, that they didn't have to go that far. And so they basically backed off and said, hey, you know what, we just need to meet these requirements. That's what we're aiming for to get our funding and then go from there. How's the baseline energy usage modeled since it was a different space? I believe the baseline was still based on, it was exactly that, it was based on an office space. And so all of the existing building inserts were for an office space versus the reference building, I believe, was considered like a residential reference building, if that makes sense. And maybe I will come back around to other questions at the end here if I have time, but I will jump into Soble because I think some of these will get answered as part of that. So I'm going to flip a little bit. So we talked about something in Calgary. Again, they were aiming for a very specific funding model. So they didn't have like a major target in terms of like an 80% reduction or more, which would be what you would consider from a deep energy retrofit perspective. But I'd like to sort of dive into one that did take that into account. So this is Soble. Before we jump into Soble, the tower, let's just talk about deep energy retrofits for anyone who doesn't have a bit of a background. Like I mentioned, it's generally an 80% reduction in both energy and carbon. So you're really looking at improving your performance after retrofit. And this is the typical kind of strategy you would use from bottom to top. So you're looking at reducing the demand. So that's a very high quality envelope, high quality systems, looking at fuel switching, and then moving on to how do we improve efficiency, heat pumps, et cetera. And that's kind of the icing on the cake is adding your renewables at the end. So that's usually the strategy for deep energy retrofit. You might have also seen it kind of presented in this manner. So this is the idea of how do we move towards like a net zero energy or a very low energy use. New buildings are usually going to start at the point where it's like they're talking about massing and shading and all of these things. Most deep energy retrofits kind of start one down because you've got an existing building. Maybe you can't change the massing as much, but you're focusing on air tightness, envelope, switching double pane windows, triple glazed, et cetera. And then you're moving down through more efficient systems from an M&E perspective and moving towards renewables at the end. That's just a different way to think about a deep energy retrofit, but they all kind of come out to the same end goal. And this is one of them. This is the Soble Tower transformation. This is a groundbreaking project in Hamilton, Ontario. So this is a post-war apartment tower that went through a deep energy retrofit, and at the time was the largest EnerPHit retrofit in the world. So we kind of had this same side-by-side for Neoma. This is Ken Soble prior to, kind of in the 60s. The tower is the oldest high-rise multi-residential building in Hamilton's portfolio, but had been in decline for several years before they even considered a retrofit or any work on it. And they actually considered several options. So they actually went through their own feasibility study that included, what if they sell it? What if they rebuild it, like complete demo? What if they go through major capital repairs, rehab, etc.? And at the end of the day, they opted to retrofit the building because they could see that they could make significant improvements actually at a fraction of the cost of a new build. So you see that the budget on this was actually $35 million to begin. So a little bit of an overview here, just in terms of who's who. So it was owned by City Housing. Similar to Neoma, the end result was an affordable housing situation. This is a taller tower, more units. But at the end of the day, they did achieve a 91% heating demand reduction and a 94% greenhouse gas emissions reduction. So that was their major target because they were looking for both passive house and or EnerPHit certification, as well as really leading. They wanted to be like leading edge on this one. And so you can kind of see where they differ from Neoma is kind of what we'll look at here. But everything starts with that assessment. So that doesn't change. So a similar role was kind of undertaken here. We were not prime on this project. We were building envelope and structural only. But the architect led this one as prime, but it did include a major condition assessment in terms of evaluating the existing structure and envelope to identify opportunities and challenges that would come with a retrofit. Where it kind of differed from Neoma is because they were targeting passive house certification, it becomes even more crucial that thermal bridging considerations are mitigated. And so those were investigated. There was a lot of thermal bridge analysis continuously during the feasibility study and then all the way through design analysis to document what the existing project's weak thermal interfaces were and then balancing an impact towards the project's total heat loss if you were to improve them, preserving thermal comfort, but then avoiding condensation risk and all of those other things. So there was a lot more focus, I'd say, put into a conversion, or there is a lot more focus put into this than it was in the Neoma conversion, just based on the fact that they were going for passive house certification. And so not only did they want to improve their thermal bridging significantly, you also have to show thermal bridge analysis for passive house certification. And the interesting one at Ken Soble was the idea of balconies. So we were talking about how at Neoma we're talking about feasibility of adding a balcony, which wasn't deemed feasible. At Ken Soble, they actually removed them. So there were balconies at Ken Soble, and they actually looked at them, and it was ultimately decided that a revision to a Juliet style construction. So that's just like a small scale sliding door, but with no projecting cantilevered balcony, would meet the passive house targets, still provide, fresh air, ventilation, ability to open up your interior. But that was the biggest change that they made in terms of the exterior layout. And you can kind of see here the during construction progress photo of actually knocking off the existing balconies. Other big difference is in deep energy retrofit, specifically passive house, air tightness testing is required as part of that certification. So an initial baseline test of the existing building is performed, and then you quantify that baseline and track the ultimate upgrade. So you do another test near the end. You can see here for Ken Soble, their final certification testing was fantastic by comparison to the baseline test and well above the passive house limit. So they were very excited about that result, kind of in tandem with the new envelope upgrades. So there's a few construction milestones kind of being shown here. So once old cladding and windows have been stripped out, they're replacing glazing with new fiberglass window assemblies in this case. And then there's actually a mineral wool installation stucco cladding or EIFS assembly. So a mineral wool EIFS that was installed over the entire tower. At the end of the day, this came in at an R38 effective wall performance. So that you can compare back to Neoma. It's about an R11 at Neoma. So that's a big difference. And that's really where you see the major change in the end result from an envelope perspective. So it's just focusing on depth of the additional insulation and eliminating those thermal bridging elements took that overall effective R value, again, from like the conversion style where we were looking at an R11 to a deep energy retrofit, we're closer to R40. Same thing, we're looking at triple glazed fiberglass windows with low E coatings. You can compare that back to Neoma, which actually at the end of the day went with double glazed aluminum framing. So there's a cost associated there, but there's also a big performance jump with that. And from a mechanical side, right, we're looking at centralized ventilation, heating and cooling, decentralized cooling boost units. They're adding ceiling fans for occupant comfort. There was a lot of changes. And again, this was an unoccupied building at the time. They moved everyone out to achieve this. And essentially it's a full mechanical gut and replacement, as well as electrically. So just to recap kind of on this one, again, this was a 94% reduction in GHG emissions. This is a future-proof design. So that was sort of the aim here. It's very impressive results, but it was publicly funded. And with that commitment from the ownership, design, team, builder, everyone kind of agreed that they were going to do something special and they wanted to really achieve something different. So what's interesting with this one is that hopefully we'll kind of see the results of it coming out in years to come. So there is a post-occupancy analysis that's ongoing with the University of Toronto and CMHC, since this also did kind of get involved with the CMHC funding model. And so I'm really excited to kind of see the end results where we can kind of compare and contrast the befores and after in terms of actual performance on this one. But at the end of the day, why do deep energy retrofit, right? It's a health impact, it's an affordability question, but you can really see some huge changes in performance with the deep energy retrofit. Did anyone have any questions there? I'm just gonna, sorry, I just have to move my mouse around a bit just to double check here, but I don't see any major questions from that one. If you do, just throw them in the chat, that's fine. If not, I will jump into my next section here. And you're going to start here with a slide that you'll recognize, but you'll notice that I chose an iceberg as our my logo here for retrofits in Alberta, because I do think Alberta is an interesting place when we talk about retrofits. Deep energy retrofits haven't really been something that have caught on here from a cost benefit analysis point of view more often than not. So we're going to talk about why. We're going to talk about alternative strategies. So deep energy retrofit, flipping back to a slide we saw before. So again, moving from bottom to top. It's about reducing demand. It's about looking at fuel switching. It's about how do we improve the efficiency of our systems, and then adding renewables at the end. Not an outrageous kind of order of events, but to truly be a deep energy retrofit, it's kind of like you can't go halfway on any of these things. You have to go all the way. Otherwise, you're not going to see the significant changes that a deep energy retrofit would kind of be accustomed to, or be, if you were going for a passive house certification, for example, that you would need to achieve to get your certification. And what we find is that in feasibility studies, that's kind of what we're seeing. In Alberta, you'll go through a feasibility study, and more often than not, the deep energy retrofit gets kind of sidelined. It's disruptive, it's costly, it's something that not every owner wants to go down that path. So we need to reduce demand. We know this. We need to reduce our HVAC energy consumption by improving the envelope so that we can resize equipment. We know this improves thermal comfort. We know this is a great thing to do, but it can be disruptive. And the struggle in Alberta specifically is to achieve a reasonable payback on energy cost. So that can be the trickiest thing for us. From the improved efficiencies. Now we're moving up a level. Again, heat pumps, switching from hot water radiator to panelized systems. This can be very impactful, but again, costly, disruptive potentially, and sometimes it requires a new distribution system to achieve using those systems. Fuel switching, again, fantastic. Switch from gas to electric, great idea, but it can be impactful where a clean grid is present, and that's not always the truth. Alberta being one of those places. So it can be tricky to make this work on paper from that point of view. And it can also require a change to your electrical service capacity, and your utility costs can be different from that perspective, especially in Alberta. So this can be kind of a stumbling block. Renewables, we are seeing that, right? Solar is great. We see a lot of it being used. There's a lot of arrays out there, but it's the last step in a retrofit. And I think that sometimes we get sidelined. It's like the solar industry did a really great job in kind of advertising itself and getting itself out there and sort of saying, yeah, put solar on everything. But it's the last step. So you can have a really poor performing building with solar on it, and it doesn't really achieve the emissions neutral pathway that we're really hoping to achieve. So that one's kind of tricky. So the question from me to you is, can we get similar results with less? What are we going to do? This kind of goes back to that idea of if we need to retrofit a building every minute, can we really retrofit every building deep energy? Probably not. We'd rather see 10 buildings, get almost all the way there than see one building get a passive house certification. And that's not to say that I would harp on it. Working on a Ken Soble is fantastic and everyone wants to be involved with a project like that, and they're incredible, but can we do that for every tower? Likely not. So I think we have to kind of reframe our thought process in that point of view. So I like this principle that was shared with me this year, the Pareto principle. So I don't even know how to say his name properly, but this is Vilfredo. He was an Italian civil engineer and also an economist and also a philosopher, because I guess back then you could be all of those things. And he came up with the principle that 80% of the efforts are the easy part, and that last 20% of the effort is the most difficult. And at the time, he was actually looking at wealth. He was looking at wealth in Italy. So it was that idea of like 80% of the wealth belonged to 20% of the population. But this principle has been applied to a variety of different things kind of over the years. But if you're wondering, like, where did that notion come from? This is the guy. So again, an introduction. This is Derek. This is Mr. Olympia 2023. You can see on the left, right? That's just Joe doing his workout at lunch break. 20% of the effort, getting 80% of the results. To get that last 20%, that 80% of the effort takes that. That Derek Lunsford here was, doing a lot more than Joe, and that last piece of the effort took a significant time commitment and cost commitment or anything else. So just to visualize that principle. So can we apply that to buildings emissions? I think so. So we've kind of coined the term a variety of people have used this, but the idea of a shallow energy retrofit. So while a deep energy retrofit is fantastic, you're looking at 80% or greater reduction. What if you get 60? What if you get 50? How about 40? Are we okay with that? That's a shallow energy retrofit. And I think that we can apply this principle to a lot of buildings, especially in Alberta, and get a good payback from that point of view. So how do we achieve this? The idea becomes basically, you need to understand demand, you need to investigate your options, and then you need to integrate that into your planning. The idea being, your HVAC systems, they can be oversized in an existing building, particularly like an aging heating system. So if you can right size that HVAC, you can give back the budget to fund a retrofit if you metered it and kind of understood, what you can do with your HVAC and right sizing it. You combine that with a more minor envelope upgrade, for example, and you might be able to kind of achieve that in a better way than, say, completely recladding the building. Next step is set parameters, investigate your options. So a big one is also just to, at the outset, define decarbonization. What actually matters to the project? Are they like Neoma, where they were just going for a specific funding stream, and so they only wanted to hit those targets? Or does the ownership have a different idea? That was really the big change between Neoma and Ken Soble. Ken Soble, the ownership, they wanted passive house certification. They wanted to go down that road. But not everyone is going to be on board with that. And even from the mindset of using terms, a lot of people might talk about net zero, but what do they really mean by that? Are they talking about energy? Are they talking about carbon? I think it's really important to understand what the project is actually trying to achieve, and then setting parameters based on that. Another big part of this puzzle is feasibility studies. We talked about feasibility studies, and I've been a part of many of them, but they can be like a $10,000 feasibility study or a $150,000 feasibility study. You really have to understand what you're asking for. So either the owner needs to know what they want, or they need like a consultant team that can really explain to them what the options are. That's kind of the difference between like doing a full-scale exploratory demolition mock-up, which is great when you're in an unoccupied building and maybe you can do that easily. But if you're looking at an occupied building, that's not as simple. So there's a lot of things at play when you're talking about a feasibility study and what you're actually going to be doing as part of that, and what you're actually going to be delivering in terms of options and final like deliverable for that owner. And then another thing to think about is, how do we integrate this with our capital planning? The introduction today was great because we learned a little bit about the retrofit accelerator, and I love that there was even the shout out to the phased approach, because I do think that that is something we don't think about, that a phased retrofit is still a retrofit. And so I think we need to kind of flip the switch in Alberta and stop thinking about capital replacement in this whole like for like, because we do a lot of that, right? Boiler goes down, replace it with the same boiler. Elevator goes down, we replace it with the same elevator. We're always doing this like for like capital replacement in terms of our funding models and how we're going to pay for replacements. Even if it's a roof, right? I'm going to replace the roof when the roof is 30 years old with the same roof. Why? Right? So we kind of have to flip the switch on that. I like that quote there, kind of like the like for like capital replacement is dead. We have to start thinking about synchronizing our facility assessments and our emissions reductions assessments, because we're really talking about the same things. And that way you can prioritize your upgrades to align, like a mechanical assessment with what the energy and emissions reductions goals actually are for the building. And then you can organize a phased retrofit to achieve those goals. And I just like this slide to kind of throw in here, just kind of from an overall idea of what really affects performance. This is something from the BC Energy Step Code Design Guide, but I like it just from the point of view of like a retrofit, is that, massing and orientation, sometimes we can't change that, but there are other things that we can look at. And even if you thought about these in a phased sense, you can really see where these affect your TEDI or your TUI. So if you don't know those terms, TEDI is essentially the total annual heating load being used. So that's going to be losses from the building envelope, air exfiltration, etc. Versus TUI, which are the orange boxes in this slide. So that is the total energy used on site. So that's how much energy is being used from sources, so like electrical, district energy, natural gas. So that'd be like space heating and cooling, etc. So what you can see here is that what is actually important to TEDI in terms of the total annual heating load, that more falls into the building envelope side of things, versus the TUI, you can see are even more so like the mechanical, the highly efficient systems, or even low carbon systems. So this is just like an interesting slide to think of from that point of view, is that something like optimizing insulation thickness, while it greatly increases your TEDI, it might not actually be as important to improve your TUI. So it's just an interesting slide to kind of consider as you're thinking about the effects on performance and how you can actually phase the approaches. And it's all about doing this in the right order, right? You wouldn't necessarily want to right size your HVAC and then do a major envelope upgrade. That would have, changed what that right sizing really meant. So this is all about kind of coordinating disciplines and understanding that mechanical and electrical really have to work hand in hand for any mechanical, electrical, and envelope have to work hand in hand for any conversion, retrofit, or similar. So just to kind of swing back to this one more time, this pyramid. So again, we're talking about reducing demand, getting up to our renewables for deep energy retrofit. But let's just take a step back and basically look at this triangle for Neoma or for a shallow energy retrofit. So same idea, but it's understand your demand, meter your data, understand what's happening, then define what is decarbonization, what is your goal. For Neoma, we're trying to meet this funding target. Then investigate your options. So that's a really well-defined feasibility study with an end goal, and then phase it with your capital planning, align it with projects that are going to be happening over the next 5 years. Not every building is going to be converted from a use and kind of give you the opportunity to do everything at once like Neoma did. When we have these buildings that are going to remain occupied, we need to think about how we do this in phases. So that's something just to maybe keep in mind from a retrofit point of view. And yeah, we've just been kind of telling this to anyone who will listen, but right, it's got to be targeted. You still have to be cost conscious, but at the end of the day, it's all about kind of this flow chart and working with it with owners around Canada and in Alberta specifically.